Training a stable critic enables highly efficient single-rollout reinforcement learning for LLMs. Traditionally, reinforcement learning for large language models relies on group-based methods like GRPO. While GRPO avoids training a critic by sampling multiple responses per prompt, it is computationally expensive and assigns the same advantage to every token. A trained critic could solve this by estimating token-level advantages from just a single response. However, standard critic-based training is notoriously unstable. This video explores Best-Practice Critic Optimization, or BPCO, a new recipe that makes critic training stable, efficient, and highly competitive. Standard critic-based reinforcement learning is highly unstable due to several key mismatches in common implementations. First, standard PPO ratio clipping treats low and high-probability tokens unevenly. Second, bootstrapped value targets can inherit and propagate critic errors. Third, a fixed GA parameter weights terminal rewards differently depending on response length. Finally, linear value heads can predict values far outside the actual reward range, and batch-wise advantage normalization forces updates even when the policy is already near optimal. These factors combine to cause training collapse. Bounding value predictions to the known reward range prevents extreme critic errors from destabilizing training. Most existing RL recipes use a linear head to predict values directly, which can produce outputs far outside the actual reward interval. BPCO solves this by applying a scaled arctangent parameterization. This mathematical mapping forces every value prediction to lie strictly within the minimum and maximum possible rewards. As shown in the experiments, this simple bounding mechanism removes extreme value spikes and allows the training reward to converge smoothly. Decoupling critic targets and removing advantage normalization prevents self-referential bias and noise amplification. Standard GA uses bootstrapped targets, which are easy for the critic to fit but often inaccurate. BPCO decouples the estimators, using a bootstrapped advantage for the policy but an unbiased Monte Carlo target for the critic. Additionally, BPCO removes batch-wise advantage normalization. Normalization rescales tiny advantages near convergence into large training signals, which amplifies noise. Removing it keeps the advantage range stable and mitigates overfitting. Adapting advantage estimation to response length and feeding privileged information to the critic dramatically accelerates learning. A fixed GA parameter exponentially discounts terminal rewards in long responses, leaving early tokens dominated by critic error. BPCO introduces length-adaptive GA, making the discount factor invariant to response length. Furthermore, because the critic is discarded after training, BPCO feeds it privileged, reward-defining information like reference answers or grading rubrics. This reduces the approximation burden on the critic without changing the policy's deployment requirements. BPCO consistently outperforms standard critic baselines and matches or exceeds group-based methods on large-scale datasets. When evaluated on the DeepScaleR dataset containing over 40,000 mathematical problems, BPCO demonstrated superior training and validation performance. It achieved a consistently higher explained variance, proving that the critic was learning a highly accurate value function. This demonstrates that a single rollout critic can remain highly effective and stable even when scaled to large, complex datasets. BPCO scales effectively to massive mixture of experts models and complex rubric-based reward systems. Testing on 30 billion parameter models showed that standard critic baselines suffer from unstable optimization and fail to improve after initial steps. BPCO, however, achieved substantially higher accuracy. When applied to rubric-based rewards evaluated by an LLM judge, BPCO variance improved faster than both group and critic baselines, proving the utility of bounded value predictions and unnormalized advantages in non-mathematical domains. Aligning the critic's output, target, and inputs with the policy signal delivers a robust alternative to group relative estimation. While BPCO assumes a known reward range and adds some training time computational overhead, it proves that the critic itself is not the weak link in LLM reinforcement learning. By carefully designing the critic's trust region, bounding its predictions, and utilizing privileged information, we can achieve stable, highly efficient single rollout training that matches the performance of expensive multi-rollout methods.